All right. So, good afternoon, everyone, and sorry for the hiccup just now. All right. So we have done the lecture in chapter 4, which is image manipulations. So let us do a very fast recap. Manipulation is about we have three types of manipulations: point manipulations, local manipulation, and also transformation. So for the transformations, is this like shear, rotation, scaling, this and that? And of course, in this chapter, I mean in chapter 5, we are still learning we would learn about the image transformation. But the image transformation is regarding to transform the image from one domain to another domain. So this kind of image transformation would be a bit different with regards to what the geometrical image transformations. So do not confuse between these two. And for geometrical, of course, it is regarding to the geometrical transformation, okay? And for the one that we are going to learn in this chapter, it would be more on the from one domain to another domain. So in chapter 2, I think, when we learn about image processing, we learn about spatial domain, right? So in spatial domain, it's a very uh, important keywords whereby spatial is regarding to spaces. When we deal with spaces, of course, spatial domain is not a must. Uh, I mean, referring to image lah, okay. Whenever any application that require, involves space, we call it a spatial domain. So the main transformation here is to transform from the spatial domain to the frequency domain, okay. So I believe you all did heard about the Fourier transform quite some times. Eventually, I think in junior year, many of the mathematics involve Fourier transform. Okay, so this Fourier transform, Fourier is actually one people. So he's a mathematician. So he proposed this Fourier transform. So the main, as I mentioned before, mostly all of the mathematical equations can be adopted and apply in image processing. Just that how we use it for what purposes. Okay, so the Fourier transform here in is to extract the low and high frequency informations. Okay. So of course, when we talk about low and high frequency, of course we have intermediate frequency lah, but that is not the extreme. So we only speak about or talk about the low frequency information and high frequency informations. So just a brief introductions, as I mentioned in last lecture. So for low frequency information, it is regarding to the smooth transition, any smooth transitions within an image. So for example, this image, the low frequency information would be the transition from the amount the apple, the color. For example, this is a red apple, okay. So the transition would be um the surface of the apple, from maybe dark maroon to light red color, and then maybe the background is white color. So there is no or little transition in the background intensity. So all this kind, so that therefore in one image, most of the time, the image information is consists of low frequency informations. And low frequency information is the dominant information that give us the meaning of this image. And the high frequency information is like higher spec, like the contrast, the how sharp is the edges, the texture, this and that. Okay, if we remove the high frequency information, we still able to describe the image, but maybe with a blur lah. Okay, which means you have a blur image. For example, you have an apple, and then after remove the high frequency information, you were able to describe, oh, this is still an apple, but then the image is quite blur lah, something like that. Okay, if you remove the low frequency information and remain only the high frequency information, you were able to see something maybe like the fine line, the texture, the contrast between the intensity, that's all. Okay, you may or may not able to describe. So that is the difference between low frequency and high frequency informations. So in this chapter, we will learn about what is Fourier transform and what type of Fourier transform we have in here. So after learning the Fourier transform, which means the DCT, DWT, and DFT, then later on in the next chapter, we will learn how to use, how actually this DCT, DFT, and DWT being used in image processing. Okay, so this chapter is, if you say it is solely about mathematics, not really true lah. As I mentioned before, I will not test you all in mathematics. Anyhow, this is not a mathematics course, so I will not testing in terms of calculation of integration, the very lengthy calculation. I will not test on that. So for this chapter, it serves as a fundamental for you to learn what is the important part in the next chapter. Okay. So image transformations, we have basically just three lah. Okay. Of course, when we talk about image transformation, we have more than three lah. But for the image processing, we only talk about DFT, DCT, and DWT, which is the Fourier, cosine, and wavelet. Okay. Image transformation maps image data from the original image into a different mathematical space via a transformation equation. So this transformation equation is the Fourier transform equations. Okay. So the spatial domain within the image alone is sometimes inadequate to process or analyze the image. Hence, transformation into another domain can provide the solution. If you want to process the data alone, for example, you want to check the intensity, the size, this and that, the common or the fundamental image processing method, then it's sufficient for you to use pixel. But let's say you want to extract some other features, especially to describe a complex object, for example, mitosis cell, for example, nucleus, then perhaps you can consider to extract features from the frequency domain. Okay. And this sometimes could be used to define a specific object, especially for deep learning training. Okay. So the input image can be regarded as a 2D signal representing two different spatial orientation, which is X and Y axis. And the output is 2D frequency space represented by a two frequency variable. So fundamentally, the frequency domain in an image represents the rate of change of spatial pixel and hence give an advantage when the problem you are dealing with relates to the rate of change of pixel, which is very important in the image processing. So this is the information that the frequency domain can provide, which is the rate of change of the pixel. Because when we analyze something, we might determine the rate of change. For example, you have maybe object A. So the rate of change is very low. And you have object B. The rate of change is very high. The rate of change, X lah. X. Is very high. So although both of these object A and object B could be looks alike, very alike in the spatial domain. For example, you have cell and also mitosis. Okay. So if let's say you have object A, you have a very high rate of change, and object B, you have a very low rate of change. So by determining the rate of change, you can actually partition the value into two different groups, and thus you can actually to perform a better classifications of data. Okay, so this is actually why sometimes the rate of change is very important. And in the spatial domain, for example, the original input image, both the object A and object B can be visibly, looks alike. But when we transfer to frequency domain, it can be totally different things. Okay, so that is why people try to use this to partition the data into different groups. Okay, so frequency domain gives the control over the whole image, where you can enhance the edge and suppress or smooth the shadow, different characteristics of the image very easily. That is because for high frequency information is actually describing the edge, the texture, all those noises are considered as high frequency information. And for low frequency information, you can actually process it. So basically, you can very easily separate the high frequency information, which is the texture, the edges, this and that, from the low frequency information very easily by just masking out the high frequency or maybe a portion of high frequency or some of the low frequency, depends on the applications. Okay. So this is the mapping or what we say, yeah, I can call it as a mapping between the contrast sensitivity and spatial domain, spatial frequency. So the y-axis here is the contrast sensitivity and the x-axis is spatial frequency. So um, this is referring to the high contrast. This is referring to low contrast. Okay. And here is referring to low spatial frequency, and this is referring to high spatial frequency. So when you look into this shading, so when you have a high contrast, which means you can see, you know, do you all know what is contrast? Which means A and B can be differentiated with each other easily. Okay, which means when you have a high contrast image, you will able to differentiate the object from one another easily. Okay, so that is why at the bottom part here, you will able to see black and white, the alternative between black and white easily. But when the image is moving upward, I mean, it, it feel like fading off. Okay, it feel like fading off because the contrast is being decreased. Okay, so this is whereby you have a high contrast region, and this is you have a low contrast region. Okay, so when we look into the spatial frequency, you can see it as wavelength. Okay, so it's just like you have a low frequency and high frequency. So that is why the gap between here is larger. Okay, and the gap between here is much more smaller lah. Okay, so you can actually see that this is, you know, something like this one, and then slowly become high frequency and higher and higher. Okay, okay. Of course, this is not a not an ideal graph because the amplitude is decreasing. Okay, so basically this is the message behind this shading the black and white lines. Any questions regarding this one, or any of you don't understand about this one? Okay, so again, bottom part is referring to high contrast, top one low contrast, whereby it appear very blur, and towards here you have a larger gap, which means I mean low frequency lah. And for this one, you have a smaller gap between the black and white lines, so showing that it has a higher frequency. Okay, so this is and this line, this curve is actually referring that the area where human eye is much more sensitive to, whereby the area under the curve is the area where the human eye is sensitive to. Of course, the human eye capability is different from one another, okay? Because my eye power is very high, I may not be, I mean, maybe my graph is just something like this. Maybe my graph is just something like this, I don't know. Maybe someone have a very better eye power, he or she may be more sensitive. But anyhow, this would be the norm, okay? The graph showing the norm of the human eye. So as you can see, the curve is rising up and then going down, okay? What is meant by this is the region where you have middle, look at this one. So human eye is not sensitive to the image with low contrast and high frequency. So that is why, since this area is low contrast and also high frequency. So and you have a graph decrease here, which means in this area, in this area, human eye is not sensitive at all, which means it's very difficult for you to see low contrast and high frequency information, because high frequency information is very fine, okay? And now the very fine information is in low contrast, so it's very difficult for you to see, okay? Just think by logic, you will know, okay? So in region, is the region whereby human eye is much more sensitive to. So that is why you would able to observe that the graph is actually going up and then falling off from here. So this region would be the region that human eye sensitive to. Why is this important? Is that we are actually, I mean, in image processing, we are actually exploring the limitation of human. Okay, if we know this the information from this region, if we know the information from this region is less likely to be preserved, I mean perceived by the human being. So what is the point that you retain information from the yellow region? Okay, which means when I want to compress an image, I will try to remove the information from the yellow region. Okay, and I try my best to reserve the information in this region. Okay, because this region is much more meaningful to human, even though you remove even though you retain the information in the yellow region, it is like not important because human eye cannot see at all. Eventually you put it there. Okay, so that is why but in terms of image storage, when we remove information from the original data, we can actually reduce the storage, reduce the size. So that is what we are going to do during image compressions. Okay, and the same thing is applied to audio compression as well. Of course, for audio compression, it has its very own graph lah. The graph is actually developed by Bell's Labs. Bell's Lab is actually from Nokia. Although Nokia is no longer the industrial player, but quite a number of Nobel Prize is from Nokia, from the Bell's Lab. Bell's Lab is very famous. The first lab, I'm not sure is it first lab, but there is a very significant lab. But until now, it still exists, the Bell's Lab. Okay, so quite a number of Nobel Prize from there. Okay, so for this chapter, we will learn about the eye and also image processing. And for, I think, chapter 8 or 9, we will learn about the audio, learn about the ear. Okay. So image with the natural world often has region of showing changes in color with sharp transition. Where one object overlaps other. In the previous image, the contrast difference across horizontal scan in the image are the same. The human eye is more sensitive to mid-frequency. Okay, mid-frequency contrast difference and high-frequency contrast difference. Okay, so that is why a human eye is able to see mid-frequency region and high-frequency region. But when we are looking into high-frequency region, the contrast must be high as well. Okay, if not, we're not able to see that. We'll be falling out from this region into that region. So high frequency in the frequency domain correspond to rapid change in pixel intensity on a short distance. So this is the definition for high frequency information, whereby how we know that this is a high frequency information is that the pixel intensity, let's say this is pixel A, pixel B. The pixel intensity changes between A and B, which is the adjacent one, is very significant. Okay, and in a rapid change. For example, you have change of color intensity from 0 to 1 in just 4 pixels. So this is considered as high frequency information because 4 pixels is very small. Sometimes some synthetic image or eventually the image is very small. It consists of 100 times 100 usually in most of the cases. So 4 pixel is very small. Okay, so a transition like this would be called or would be known as a high frequency information. And high frequency information tend to be noise, sharp edges, boundary, or very fine texture features. So these are the example of the high frequency informations. And yeah, So noise are considered as high frequency information. So actually you can correlate when we learn something like this. You can actually correlate why using mean filter and using median filter can remove noise. What is the effect after you apply mean and median filter? Blur out, right? Blur out is the way to remove high frequency information. So that is why salt and pepper, those are high frequency information and those are noise as well. Because why? Because salt and pepper usually corrupt only 1 or 2 pixels in adjacent. Okay, so when you corrupt 1 or 2 pixels in adjacent, and you are actually fulfill the definition of high frequency information. So when you fulfill the definition of high frequency information, you will be automatic under this category. And mean and median filter is actually trying to smooth out or to remove all this high frequency information. So that is why when you know that even though you have some other filter, maybe a filter X, and the filter X is the capability of filter X is to remove high frequency information, and now you have salt and pepper noise. So basically, you can correlate all this. You don't need to. Let me try the filter first. You actually don't need to try by looking at these features of the filter. You can actually know, oh, this can be resolve the salt and pepper noise. Do you understand? So something like that. So this is what I look for. This is what I look for. I wish to teach you all about the fundamental, and then later on, because in industry we have uh, different kind of challenges coming in and different requirement from different customers. So it's impossible for you to learn case by case. Okay, so you have to know some basic. So later on, when your boss asks you, oh, you try to propose a method lah. So you will not. I mean, yeah, of course, I understand most of the time we try and error lah. Okay, or we just Google it and see if any issue, possible answer from the internet. I think that would be 80%. But later on, after that, you still need to explain to your customer, ma. So when you try to explain that is how you correlate this. Okay, so this is what I'm looking for, to be frank. Okay, and this is what I'm going to test as well. Okay, so no matter it's open book test or face to face, the question would be still fall within this region. Okay, so even open book test, I don't think you will get the answer. Okay, so but anyhow, for physical exam would be closed book and no open book. Okay, so most nature image have large features which change relatively slowly. So most of the information in the low spatial frequency range. Okay, so for those nature image, which means those image that you capture using any mobile phone, any DSLR or whatsoever. For example, this is a nature image. When I use the word nature, which means it is not synthetic. Okay, what is mean by synthetic? Which means I declare each and every pixel individually. For example, pixel 1 to 5 is black, 6 to 11 is blue, something like that. That one is considered as synthetic. Okay, and this is called this Lena I think .jpg or TRF. This image is considered as the natural image lah. Okay, so it is in grayscale and in spatial domain. Spatial domain, which means in x and y axis lah, y axis and x axis. Okay, so this is a frequency domain using the DFT. Okay, so again, of course you can actually. Sometimes it is very tricky for you to recognize and DFT. I mean, after Fourier transform, because in MATLAB, you actually need to, move this square around. Actually, this is from different square. They are moving around so that you have a low frequency at the center and high frequency at the boundary. Okay, there are some tips and tricks over there. Okay, but we are not going to learn this one. But so by default, this would be when you look into this type of image, you would expect the center part would be the low frequency, the outer part would be the high frequency information. Okay, so of course you might see something like the light. When you look into this one, actually you can source, you can see something like, there is sort of star over there. Okay, I will explain about this light later on. Okay, there is, again, this light, they do encrypt some information over there. Okay, it is not simply just a light over there. Okay, so in general, the expressions time domain and spatial domain refer to the domain of the original or given signal, which is 1D or 2D lah. So this is a time domain where you involve the time and also amplitude, and this is a frequency domain where you actually look at the like sliding a cake from different direction. From the top direction, you will see a different layer. But if you slide something like this one, you will not see the layer, but different view lah. Okay, so frequency domain is actually sliding at this view, and that is why you have a DFT or DCT or DWT lah. Okay, this is the transform, but why is it discrete? Because when you're sliding at this directions, you were able to get discrete value like this one. Okay, but for this one, this is not discrete. This is continuous because you have time. Okay, but for frequency, usually you only have a discrete frequency value. Okay, so the pattern of this image in the frequency domain is obtained taking the DFT of the image. The frequency domain is not readily prepared to understand by your human brain. So at least from visual perception, our eye cannot understand. So that is the reason why we cannot understand the image. Okay, by looking into this, you will never know the original image is like this. Okay. So any questions from the previous introductions for Fourier transform? Now we will start with DFT and then followed by DCT and DWT. Okay, so basically the reason, the theory behind the DFT, DCT, and DWT will be more or less okay, just a little bit, advanced level a bit okay. So Fourier transform is about mathematics. Yeah, to be frank, Fourier transform is all about mathematics. Okay, and before we understand DFT, we need to start with the sine wave. Okay, starting from here, if you feel confused, doubt, please raise or let me know. For those online, maybe I cannot view your chat. If you have any questions, you may use the raise hand button. Because I hope you all can follow my pace starting from this slide. Okay, because it's a bit difficult to understand. Okay, I try my best to illustrate. Okay. Okay, so this is the general equation, not really general. Anyhow, to start any DFT, DCT, DWT, we need to start with the sine wave. Everything regarding the sine wave. Okay, I believe you all know the sine wave, which is something like this one. Okay. So we follow the slide first, and then later on I will explain how it is being connected. Okay. So the first one, we have a K value, and K is 3. Why it is 3? Because 1, 2, 3. Okay, is it clear? 3. So when you have K is equal to 4, 1, 2, 3, and 4, and 6, and 30. Okay, so this is the K is actually referring to frequency. The frequency. So when you look into the image, when you have K is at the peak, so you will have white color. When your K is at the bottom, you will have black color. So this is why you have this black and white strip. Okay. So when you have more and more frequency, you will find that the strip is increasing as well. Why? Because when you have more and more frequency, each of the peak would contribute to one white strip, and each of the bottom, what we call this one, we will contribute to one black strip. That is why you have the black strip is very far away and then continue to become a lot of white and black strip. Okay, so this is K. Okay, and now we have an A. Okay, so A is actually referring to the amplitude. So when you have A, for example, this is 1 and this is -1. So when you have A in full length, A 1 to -1, you would have a bright image. So when your A is reducing to 0.5, you will have a dim image. And then later on, dimmer the image, the darker the image lah. Okay, so this is how amplitude affect the sine wave. Later on, we will have another things called phase. Phase is actually transferring, not transferring, but moving the white and black and white strip forward and forward. So you will see this is the starting point, and then later on, when the phase is become 45, you will find that the starting point is here. 90, the phase is here. 135, the phase starting point is here. Can you see the difference? Which means the white and black strip is actually moving towards your left-hand side. Okay. So when you have 180, the phase is actually here, and then continue, moving this way. And you will find that after the last one, which is 360 degree, the phase is actually same as this one, the origin 0. Okay, because you move one round. Okay, so that is actually what is the phase affect the entire sine wave. Again, previously, do you still remember you have a K here, which is referring the frequency? Now you still have the K here, but now the K is a vector. What is mean by vector? Which means you have A, B, this is vector, okay? So when you have a vector, so when K is equal to 30 degree, which means your line no longer is in vertical, but rotated by 30 degree. 60, rotated by 60 degree. Okay, so this is the difference and also the effect of this, different amplitude, phase, this and that. So this is when your K is, when your K is a vector, whereby you will contribute the informations of frequency and orientation. So frequency is how frequent is it, and the orientation is like something like this one. Okay, so when K is a vector, so you will have the frequency orientation, amplitude is represented by A, phase is represented by this one, okay, the symbol. So after that, you will you will form this one. So this is anyhow, the Fourier transform is not exactly the real image. For example, you have A, original image A lah, then you Fourier transform to become A prime lah, okay? A prime is actually just an estimation of A, because you can never get an A. You are just converting something else to, the original image to something else. Both are, nearly the same, but not identical, okay? This is the reason why you have a real image. This is a sine wave. In real case, it is like a step function. But in the sine wave, you have only this one. So when both of these A and B, superimposed together, you will get something like this one. So what data you have been lost, which means all the data from here is the data you don't have. So that is why we call this sine wave or the DFT, DCT, or DWT is just an estimation. Okay, so that is why in real case when you have a step function like this one, you would expect to have a very high contrast image, because white color, black color, white color, black color. But this one, you are just an estimation. You are losing all the data from this gap. Okay. But of course, the mathematics did not stop here, because this is not it's unacceptable to give you this conversion. So we try to sum up all the waves together to approximate the final image. So this is one sine wave. So we sum up with another one, higher frequency, and we sum up with another one with higher frequency and continue. So that is why when we sum up with not infinity but a specific number of many sine wave, you were able to get this one, which is very, very likely to the original one. Okay, how is it being done? So this is the original wave, which is red color, and the high frequency wave, which is purple color, and the sum one is black color. Okay, so when you have the original sine wave, which is something like this one, then you add in, I mean plus in another high frequency wave, because high frequency would have a more wavelength, so more wavelength. So when you have more wavelength, this is peak point, right? This is bottom point, right? So this one minus from this one, so you will get somewhere around this. You will pull the signal downwards, okay? Because you affect it, you will pull the signal downwards. So later on, when you add in more and more high frequency, you will actually from something like this one to something like this one, and then later on slowly become something like this one. Okay, so this is how we try to estimate this image, and later on you will get something like this one, which is very, very similar to the original one. Okay, so when you have an infinity amount of this adding up, you can approximate the black and white strip pattern, which is the real image. Of course, this is a very cliche example because you only have black and white strip, but in real case you have the natural image, okay, which is different. Okay, so for any questions from here, I mean, what is K, what is A, what is what is phase? Is it clear? All right. So this is a process where we use collection. We use the word collection because we need to use a lot of different sine waves summed together to approximate the original image, or a collection of different spatial frequency to describe a real image. We can actually write the mathematical equation like this one. Okay, so fx is actually the original of a collection sum or different spatial frequency, and gk describe the amplitude and phase of this function. So sine would be the sine wave lah. This one is one set lah. So this is the original image, and this is the image after we convert to the frequency domain. So the position of this spot describe the spatial frequency. So actually there are spot over there, these are spot. The frequency of the spot describe the position describe the spatial frequency. The intensity of the spot describe the amplitude. And this example did not consider the phase, which means I did not include the phase, which you should, rotate something like this one, 30 degree or 60 degree lah. Okay. So the position is actually referring to the spatial frequency, which is the black and white strip, and the intensity of this is referring, how bright is the white dot or how dark is the white dot is actually referring to the amplitude. Okay, so note that the fx is the real image, this is the real image, and gk is the collection of sine wave that can be summed up into this one. Okay, so which means the fk is fx is the original image, and the gk is the collection of sine wave where we want to sum up to approximate this fx. Okay, so the process to derive gk from fx is called Fourier transform. Okay, so now do you understand what is Fourier transform? Which is to get this one from the original one. This process we know it as Fourier transform. Okay, so basically Fourier transform involves the conversion from spatial domain, which means something that human eye can understand, into the frequency domain where you might not able to understand, may or may not lah. Okay, but most probably you cannot lah, because the information displayed by the Fourier transform, the frequency domain is not something that is understandable to human lah. Okay, so fx is the original image, which is the real space, and gk is the Fourier transform, which is the frequency space lah, which is the result of Fourier transform. Okay, so I did mention this example in the last lecture. So the region close to origin has short k vector. So basically the k vector is like something, this one, okay? So this is the k vector, which means the vector is starting from the origin, the center lah. This is the center. So this is the k wave, this is a vector lah, okay? depends where is it lah, which direction is it the vector. So the region close to the origin has a short k vector, which describes low frequency information. And the region far away from the origin has a long k vector. Why it's short or long? Because, this is short long, this is long. Okay, very simple. Okay, that is why you have a long and short k wave. So this is the original image, which is the Fourier, and this one is the Fourier transform, which is in the frequency space. And this is the original. So when we mask away the all the high frequency information and retain only the low frequency, you will still able to describe, oh, this is Fourier, or actually this is an English man. But of course, as I mentioned previously, all the great details, the hair, the details on his clothes, the expression, the eye, the wrinkles, all are missing lah. Okay, so that is all these are considered as low frequency information. And when we mask out the low frequency information, retain only the high frequency information, you can only see, something like this one. Okay, you can't even tell this is a male or female lah. Okay, so that is the high frequency information and low frequency information. So the 2D DFT is given by this equation. So basically, it is still a sine wave lah, 0, 0, and then start to 0.707, and then back to 1, and then coming down back, and then you go down. Okay, 0, 707.1, and then going back down, 0, negative, something like that. Okay, to become a one wavelength lah. Okay, but of course this is you don't need to memorize this one. Okay, here comes the explanations for the color here. Again, this one you're able to see, right? This one is much more clear. You will see like, a star, at the center, right? Whereby this is brighter, and there is a line here, very bright. Some line here very bright, like like you are looking at the skies. This is the sun, something like that lah. Okay. So why they are this difference intensity? So this chart will explain. Okay. So let's say this is our input image, whereby you have a white color dot at the center, and the rest of the background is black color. Okay. So of course, you would have low frequency information. So for this one, although this is very simple, but low frequency information would be all the black pixel and all the white pixel within this strip. Okay, what is the high frequency information? Then that would be the perhaps it's very difficult for me to draw. Let me use red color. The changes here, the changes from black to white color. All these only these four are considered as the high frequency information. Why? Because there is a rapid change of intensity within a very rapid time. Okay, so since recall back the center of this is a frequency domain. So the center point, the origin or the center is the low frequency information. Since we have many low frequency information, so you would expect the center point of this figure in frequency domain would be very significant or very high contrast. So let us understand the scale over here. When you have low energy, which means you have little or no this information, little or without this information. So when you have high energy, so it shows that you have a lot of or abundance of this kind of information. So this is illustrated by the color, whereby you have a dark blue or eventually black color, which means you have little or none from this information. So if you have a red color or even eventually maroon color, it shows that you have abundance of this information. So when you look into this Fourier transform, you will find that the center point is red color or in maroon color. Why is this red color or maroon color reflect? It is mean by this in this original input image, you are actually having a lot of low frequency information. Why low frequency? Because origin is regarding the low frequency information. So let's say you have another image whereby there is red color over here and blue color at the center, which means you have very, very, very little low frequency information and abundance of high frequency information. Do you understand? So this is the way we illustrate the amount of data you have from the input image. So when we convert this one to something like this one, whereby you don't have red or blue lah, okay, you only have uh, 0, you only have 0 to 1, whereby 1 shows that you have actually the same lah, the scale is 1, this is 0, which is white color, which is black color lah, okay. So this is high energy and this is low energy, okay. So looking at this one, you will find that, oh, actually the original image has a lot of low frequency information. So that is why at the origin it's very bright, okay. What color, what information is very less in this input image? Somewhere around here, whereby high frequency information is not that, not that much, but it still got high frequency information. Why? Can you see this region? This region. So this region remarks that in the input image, they are actually exit some of the high frequency information. Okay, but of course, in most of the case and practically, you will find that the origin would be brighter because it's not logic that in one natural image, all the intensity changes is very severe. If you found that this the frequency domain, the low frequency image information is very, very less, and high frequency information is a lot surrounding the box. You can actually deduce that this is a very noisy image. Why? Because noisy image is always in high frequency information. And if the image, input image is being corrupted severely by the noise, you would expect the high frequency information would be dominant and the low frequency information would be very less or eventually none. Okay, so that is the reason. And again, this is something you can correlate lah. Okay. So any questions so far regarding the frequency domain and the frequency domain and the spatial domain? No. Okay. So later on we will have another one. Actually, this one is same as something like this one. It's actually the same, just that it is being illustrated using color map. Okay. We also call it as a color map. Although I know that for index image we use color map, right, or the lookup table, right. So actually color map is something, you color up something else and then that is a map, so you call it as color map. But okay, so this is actually the color map. Actually you just converting the high frequency, originally is white color, you convert to red color, and then later on is in the low frequency, the low energy is in blue color, that's all. Okay, so you can actually define this scale by your own. You can play around using MATLAB. So from this image, you can see that the high frequency information is still a lot because you have that color. But the low frequency information, which is surrounding the boundary of this square, would be less. Okay. But nonetheless, that is why you have a very small transition of intensity here, eventually here, some part of here. Okay, so that is why you would expect something like this one. Okay, so most of the image pixels are smooth and contribute to low frequency information. So that is why you have a red color at the center point. Sharp edges usually contribute to high frequency information, and the boundary is the high frequency information. So for the figure above, the frequency domain now shows some component in the middle to high frequency region. However, the the bulk of the color is still concentrated at the low frequency region. That is because most part of the image is grayscale variation is smooth. Okay, so an image of a very fine texture, or an image corrupted with noise, especially for example, salt and pepper noise, will show more component in the middle to high frequency region. So you can actually say that this is, of course, there is no clear cutoff point, but you can actually say that closer to the origin would be low frequency. This part would be high frequency, and this part would be middle frequency. You can actually, partition it yourself. But there is no fixed cutoff point over there. Okay. Any questions so far? Can I understand now? Mm, okay. Can DCT and DWT is something, I would say DCT is important. DFT is the fundamental. DCT is something important to be used, whereby for image process, the JPEG that we always use, .jpg or .jpeg, it is actually a very cliche extension for image compressions, which means you can compress an image from a very big size to a very small size. So what method is being used is DCT, discrete cosine transformation. So this discrete cosine transformation is somewhat more or less same as the DFT, okay? And then later on, when you, I'm not sure if you're all aware, actually you will have another extension dot 2000 JPG, I think. I think the name is dot 2000 JPG or dot JPG 2000. I forgot already. That is actually another version of JPEG compressions, but that one is using DWT. Although the overall performance of DWT or 2000 JPEG is much more better than JPEG, but nonetheless, JPEG is much more common to the society. So that is why eventually the manufacturer did not consider to put this extension in. Okay, so when you look into the extension of the image, you will roughly know, what type of compression method they are using. Okay, as long as it is using .jpg or JPEG, it is using DCT. Okay, what I want to highlight DFT is that DFT is the fundamental. DCT is what we are going to use, which has the same, not same, but more or less the description as the DFT. And DWT is something advanced. Okay, and all these three are being used in image compressions, which will be teach in the next chapter. Okay, we take 5 and then we continue to DCT. Okay, let us continue. Okay, as I mentioned just now, DCT would be the core of image processing, whereby it's important. Okay, it's important. Okay, so this is cosine transform DCT. So the DCT transform help to separate the image into parts or spectral subband. Actually, the application is same as the GFT, but then in DCT we are more towards the application in image processing of differing importance with respect to image visual quality. So later I will call this as DCT. Okay, DCT is similar to GFT, which is the discrete Fourier transform, such that the DCT transform a signal or image from the spatial domain to frequency domain. So DCT is an important step in image compression, which is the JPEG compression. Okay. So DCT can approximate lines well with fewer coefficients and is computationally simpler than GFT. Okay. So this is the advantage of DCT over the GFT, whereby it has a fewer coefficient and is computationally simpler than GFT. Because in DCT, because you have to know, although we say, we only compress one image, but when we compress an image, we are dealing with all the pixels. So in one image, although the image is very small, we have many pixels, like maybe 200 times 200, you have more than 1,000, maybe 10,000 pixels. So in order to simpler the computation is very important. So the one dimension DCT is defined as this one, and the corresponding inverse of one dimension of DCT as is simply just this one, okay, between F inverted inverse. So this is the two-dimension DCT whereby we are going to use, because image is a two-dimension, and the output of DCT is called DCT coefficient. Okay, the DCT coefficient represents the energy distribution of the image from low to high frequency. So can recall energy distribution, the energy map, which is from low energy to high energy. So the high frequency information is to describe, this is the high frequency, this is the origin, which is low frequency information, this is the boundary, which is the high frequency information. So it is important to remark that human eye is more sensitive to low frequency information. So that is why we are able to understand all the information well. When we remove all the high frequency information, we still can tell that this is an apple, but then the apple is very blurred, that's all. But if we remove all the low frequency information and retain only the high frequency information, you may or may not be tell that this is an apple. Okay, so this is the example of DCT coefficients with an 8x8 array. So also note that aside from the DC coefficient, the rest of the coefficient are known as altering current, which is the AC coefficient. The DC coefficient is always much more larger than the AC coefficient. Basically, in one image, you only have one DC. This is the DC, which is at the top left corner. And the rest, we call it as AC. Okay? And if you're aware, the DC coordinator, the DC coefficient is much more larger than the rest. Okay, much more larger than the rest. And also, this towards this region, it is referring to the low frequency information. And towards this region is referring to high frequency information. So, as you can recall, most of the nature image, it has higher value of low frequency information, but the high frequency information would be less. So that is why in most of the time, the DC value here would be much more larger than the rest. And you see the rest would be 0, 0, 0, 0, and you some value here, eventually the value is very, very small. Okay. The DCT coefficient shows how much the particular component contribute to the 8x8 image, and the component with a value of 0 which means contribute nothing to the image. So we have 8x8 why we will have, in DCT or in image compression, we will always emphasize 8 times 8. Why 8 times 8? Because 8 times 8 is the size of the block selected by JPEG. JPEG is actually a group of people, a group of community. So they are actually the one who are very expert in image processing, and they think that 8 times 8 is the process the JPEG compressions. Okay, so that is why in this chapter and also the next chapter, we are going to process the image conversion using 8 times 8. Okay. The intensity with low frequency informations will be in the red color, and the one in green color will be high frequency information. Of course, the way I partition it, the red color and the green color is also depends. Okay, you can actually partition it something around here. But the main point I want to let you all know is that towards this point is low frequency information, and towards this point is high frequency information. The same thing like the Fourier Transform, the frequency domain. At the origin is the low frequency information, and at the boundary would be the high frequency information. There is no such solid partition or this is low frequency, this is high. No. Okay, I just want to let you all know which extreme represent what data. Okay, in Fourier Transform, Fourier frequency domain, the origin is the low frequency information, the boundary is the high frequency information. And for DCT, for emission, towards this point is low frequency information, towards this point is high frequency information. Okay, so and also you would aware that the frequency of towards low frequency would be higher, the value would be higher, and towards this side would be lower. And also in the DCT coefficient, we will know the first one as DC coefficient, the rest as AC coefficient. Okay. So this is the resulting. This is the resulting transformation matrix round to 2 decimal place, and this would what the DCT looks like. Actually, when you look into this one, this is towards the x direction, this is towards the y direction. But when you look into it, it's actually the first image is actually a flat image. What it means by flat image, which means there is no change. Anyhow, in DCT, DFT, or DWT, we are actually looking into the rate of change. Still remember, high frequency is the information, the pixel, whereby it has a high rate of change in terms of intensity, right? So low frequency would be no or very low rate of change across the pixel. Okay, so for the one in the top left corner would be the one with flat image. What is called flat image? Which means no changes in terms of intensity. That is why you have a flat image, flat color, which means you only have the fixed color. When going towards this x direction, you will find that the frequency is increasing. So this one should be a flat color. So still remember, white color is the rising edge. Black color is the falling edge. So for this one, you can actually assume that this is a rising edge and falling, something like that. Do you know? This is still a sine wave. And then for this one, you will have a rising edge, falling edge, rising edge again. Rising edge again. Rise, fall. So this is how you get this one. So when you move towards the x direction, you will find that the frequency is higher, higher, and higher. And for the y direction, it's the same, but in the y direction. So that is why you will have something flat image, white, black, white, black, white, something like that. Continue until this one. Okay. So when you sum up the waveform, this waveform and this waveform, you will get something like this one. Okay, and you sum up this waveform with this waveform, you will get something like this one. So actually, we are using the black and white strip to illustrate that. So that is why you will find that at this part, you will find that this is look like a checkerbox. Okay, because you're summing up the wave. But of course, it's somehow very difficult for you to understand how it's being summed. But when you know the principle, this one sum with this one. No. This one sum with this one. you will get something like this one. Exactly like the graph I showed in previous slide. Okay, so this is how you actually summing out and you found and you know from x and y axis so that you will get all these kind of blocks. So if the image has only this component, this bullet point, if the image has only this component, the image essentially changes from white to black color. Okay, so each of these is not simply a block, but to remark that what is the rate of change in this image. Okay, so if you have all the image, I mean, if you have a very high, value in terms of in this position, so which means the entire image is actually changing from white color to black color. Okay, if the image has only this component, which means the image is a flat image. For example, you have a totally white or totally black image. You would be, I mean, after you convert to DCT, you would be able to get maybe 4, and then the rest of the 8 times x block is 0. Actually, this one you will get something like this one which is 8 times 8 Okay, so if you have a flat image, for example, total black or total white color, you would be able to get maybe this one is 4.0, the rest is 0. Because why? Because you only have the flat image color. Only I mean you don't have any other component already. So if you have only, for example, 8 times 8, you have only 4. The rest is 0. This is 8 times 8. So which means your entire image is changing from white color to black color, which obey this one. Okay, so this is actually the message behind this block okay. So if you have a half wave of A wave, which is A wave, and a half wave of B wave, so basically 2 waves sum together, you know. This is A wave, this is A, this is B. So later on you will get the white line, which is the sum wave. Okay, so that is the sum wave here is actually this image. Okay, that is why, you know, originally you have -1 to 1, right? So after that you reduce in size, right? I mean reduce in amplitude, right? So that is why the output image here is a bit dimmer. Okay, so that is why you also would aware that the image here would be brighter, the image here would be a bit dimmer. Okay, because of the summing up the wave, you might have different amplitude or you change in amplitude. Okay, so this is of course, I hope you all know the background, why this, I know all these checkerbox, how it is coming from, and I mean, the reason behind. But of course, you don't need to, you know, I give you 2 or 3 waves, you sketch me the last wave, not something like that, okay, crazy. Therefore, to create any kind of 8 times 8 image, what you need to do is to determine the combination of all these components at the same time in all channels. For example, YCBCR. YCBCR will be one of the color model required to use, especially in televisions. Okay, so each of the component is weighted based on something called Dct coefficient. So the Dct coefficient is a number representing the contributions of each of this individual component to the whole, which is 8 by 8 pixel group. So for example, if the contribution of C is 0, C is this one, then there is no part of the cosine in the 8 times 8 image we're looking into this image we are looking into. If C is 0.1 and A, this is A. If this is 0.1 and this is 10, which means C has 100-fold less impact on your input image than A. So by using this Dct coefficient, we can actually know which component is the dominant component in our input image. So later on, if C is not so important, so we can omit C. We can throw away all the information from C. Okay. So in DCT, we are actually calculating the coefficient for this wave. So in JPEG compression, the main purpose is to compress an image to remove some of the high frequency information and retain the low frequency information. The degree of eliminations depends on the desired output quality, because most of the time when you compress an image, you can actually control the compression factor. So the higher the compression factor, the greater the compression it is. Okay. So the high frequency cosine wave component at the bottom right of the basic function of DCD does not contribute much to the image. So which means you can remove that one now. Okay. But sometimes maybe some of you might ask, why we just don't remove all the high frequency information? Because we want to get something very, the so-called optimization. Optimization is a keyword, and in many research, optimization is something, even the least trade-off for the best we can have. Okay, so that is called, we want to buy the best computer using the minimum money. Okay, so we cannot say, okay lah, just give 3K, settle everything. Of course, that one is a borderline or boundary. It wouldn't be the optimized one. So by using DCT, we can actually optimize the trade-off between what information to omit and what information to retain. Okay. So the basic operation of DCD is as follows. The input image is n by m, which means you have a 2D. So Fij is the intensity of the pixel in row I and column J. Basically, is x and y exit. So Fuv is the DCD coefficient in row Ui and the column Vj of the DCT. So for JPEG compression and MPEG video, the DCT input is usually by 8 by 8. It's an 8 by 8 or 16 by 16 array of integer. The image is not exactly multiple for 8 times x, but it will temporarily pad out with to that size. Okay, again, there would be padding happen if the image, it is not the division of 8 times x or 16 times 16. So you need to pad out, okay? Depends on what padding method you are using. So the array contains each image window, respect color and band pixel level. So if you have a color image, for example, RGB, you are actually perform the compression in all layers, R layer, G layer, and B layer. Okay, you will not compress in the original RGB color. So this is an example of DCT. This is the original pixel value. This is actually 8 times 8. So basically, this is the, in one image. So you extract one block. In one original image, you extract one block 8 times 8, you will get something like this one. And then you convert to M. How you convert to M? You are actually minus by 128. Okay. Why minus by 128 is actually a Nyquist theorem. Again, Nyquist theorem is developed from Bell's lab. Okay, so this is obey the Nyquist theorem, whereby if you want to approximate the waveform, you just need half of the input information. Okay, we will learn Nyquist theorem in audio compressions. I think in chapter 7 or 8. Okay. But for this one, it is because of Nyquist theorem. So that is why the value here is actually minus by 128. You minus 154 with 128, you will get 26. Okay, so you minus 123 with 128, you will get -5. So that is why in DCT value, you will find that, why there is a negative value? Because over here. Okay, this is the reason why you get negative value. Okay, so as the DCD is designed to work on a pixel value range from -128 to 127, so therefore the origin board is leveled off by subtracting 128. Okay, because in Nyquist theorem, we just need half of the value, which means you don't need to put 0 to 255 and then 0 to -255. Instead, we cut it into half, which means you level off it, push it to another half side, which means the original is 0, 255, something like this. You pushed it up, move the entire thing downwards. So you will have a 0 point here. You will have 127 and -128. So now you have something like very, very similar to sine wave. Okay. So this is how we actually the reason why we want to -128.
Okay, M is the shift block. We call it a shift block because we already minus off 1 to 8. Shows the result matrix after the subtraction. So the resulting transformation matrix round to 2 decimal place. This is after you perform DCT. And the DCT value is actually this one. Okay. Which can accomplish by the so this is the equation for you to get the DCT value. But of course, most of the time, you just need, I think the core function is called DCT lah, in MATLAB. Okay, it's very simple lah. And I don't really need you to calculate lah. Okay, as long as you know what is the basic principle. And of course, we will have the flow in next chapter, which is chapter 6 lah. Okay, for this chapter, we will not discuss that part yet because that part is unique for JPEG compression. So noisy data is usually in high frequency, but of course, again, not all high frequency information are noisy data. Okay, in noisy audio data might have many spurious peak over a short time scale. So this is also the definition for high frequency information. So if there are many rapid transition over a short distance in intensity from high to low and back again and vice versa in an image, we can suspect there are possibly 40 pixel. If the 40 pixel is a lot, which means we can actually deduce that the image is being corrupted by noises. Okay, because it's not so logic to have because an image should bring different kind of meaning to human being. So if your image is considered of random noise, then that shouldn't be something useful or meaningful to human being. Okay. It is important to remark that not all high frequency data are noise. So this is very important. Noise, because noise fulfill the definition of high frequency. So basically, the noise would be a high frequency information. But of course, not all high frequency information are considered as noise because you have a sharp edges. So these sharp edges could be a very significant high frequency information. Therefore, noise will contribute heavily to high frequency component of an image when it is in the frequency domain. Okay, so also if you have you have image corrupted by noise, and then it's very difficult for you to remove pixel by pixel, especially sometimes when you use filtering, because filtering is local operation. You may need to consider the neighborhood pixel. So sometimes it's not easy for you to remove the noise from the local filtering method. So sometimes from those for this kind of image, you can convert to Fourier transform. I mean the frequency domain, and then you remove the high frequency information and convert back to spatial domain. You will find that all the noise is being removed nicely. Okay, so this is the magic over there. Because we reduce the high frequency component using low pass filter, we should be able to reduce the amount of noise. Okay, maybe we will not able to remove all the noise, but most of the noise. The MATLAB code of the next page shows the DCT transform applied to 8x8 image block, and the pixel value is replaced by the average pixel value in the subblock. So this is a function BLK Pro, which means it's the block processing. Okay, this is just for information. I don't think you are going to use this in lab or assignment. Yeah, I don't know. Okay, so this is the coding. I am the built-in image, and then block processing. I is the input image. 8x8 is the size of the window. Either 8x8 or 16x16. This is to get the mean image, which fulfill average picture, which to do this action. Okay, and then I'm show this one. So this is the image after the compression. So sometimes when you if you are going to compress an input image with a very high compression factor, for example 10:1, you will find that the image will be a bit blocky feel. Or else for those images like a low resolution image, when you zoom in, you will find that why this image like one block. The blocky field is actually from 800 pixel group. Okay, this is the reason why you will get a blocky field, especially when you zoom in a blur image. Okay, of course, the blocky field consists of 800 pixel block, not the pixel itself, not one pixel. Okay. Okay, so that is all for DCT. Any questions? No one. Okay. Will I teach too fast? Still okay. Okay. If I'm too fast, please let me know. Because sometimes I might be getting more and more excited when talking. Especially something that, yeah. So please let me know if you feel like too fast. Okay. Okay. DWT. DWT is another transform that we are going to discuss in the next chapter. As I mentioned just now, DFT we are not going to use, but DFT we are going to discuss in this chapter is because the fundamental in DFT is very important to understand DCT and DWT. Okay, but in image processing we are going to use DCT and DWT. Although DWT is not so common to the society, but then DCT is the, because DCT is using in JPEG and DWT is using in JPEG 2000. Okay, so and actually DWT is better, better performance than JPEG which is DCT but then the popularity of DWT is not that high. So that is why we learn these three, of course, because still need to aware of it. DFT, DCT, and DWT. Okay. So can recall the reason. The benefits of DCT against DFT. The benefits of DCT against DFT is that the DCT is much more simpler and less coefficients to calculate. So the overall computation method is easier for DCT as compared to DFT. Okay, and DWT has another advantage over the DFT and DCT. So in the DFT and DCT, once we transform the image into frequency domain, we no longer have the spatial information. This is correct. This is because you are transferring the entire things into another domain. After you transfer to this domain, you no longer have information in the original spatial domain. Okay, so this is a trade-off either way, left or right hand side. Okay, so in DFT and DCT, when you transform, you will lose all the information in spatial domain. So that is why if you want the information, you need to store it first and then later on transform to another one. Okay, but the Fourier transform has a drawback dealing with just frequency component in the signal. The temporal details are not available. Temporal is actually spatial domain. Okay. The Wavelet Transform combined with the filter bank technology and address this weakness, which means in DWT, you can have both of these information, spatial domain and the frequency domain, or the temporal domain. Okay, temporal domain and also spatial domain is the same thing. Temporal is regarding time domain. Okay, so in terms of this image processing is the same. So a wavelet is a ripple signal meeting certain characteristics. So wavelet is actually little wavelet. Function that are concentrated in time as well as the frequency around a certain point. It is used as the basis of the transform just like the sine and cosine and are used in Fourier transform. So this is the illustration of the continuous wavelet transform, whereby you will have something like this one. You are actually, a change of a little wave. Okay, so which means you have a sine wave, and then later on you have a sudden change in the frequency. So that is why when you convert this into black and white strip, you will find that the display is a bit different. You can't really describe that this is what, but from the sign and but from the sign wave, you can actually tell that it is suddenly changes here, okay, at a particular point. So Fourier transform is the superposition of sine and cosine with different amplitude and frequency. So in other words, the wavelet transform is the superposition of wavelet with different translation and dimension. Okay, for an image, the output of the wavelet transform show the energy distribution, which is the frequency domain of the image, as well as the spatial relationship, which is the spatial domain of the image in a spatial scale domain. So this is the main advantages of DWT, which means it holds the information of frequency domain and also the spatial domain. Unlike the DFT, the DWT in fact, the DWT refer not just a single transform, but rather a set of transform, which with a different set of wavelet basis function. So the important properties of DWT is that wavelet function are spatial localized. Wavelet function are dialectic, translated, and scale version of a common mother wavelet. It is hard or Dubachis. Each set of wavelet functions form an orthogonal set of basis function known as a daughter wavelet. Okay, so basically you will need a mother wavelet and then you form a daughter wavelet. Okay, basically from something dominant and then from something subset of it. So two dimension of DWT is a particular interest of image processing. Always, as usual in image processing, we are always deal with two dimensions. So overview of the two-dimension DWT process would be this one, step 1, 2, and 3. Apply one-dimension DWT along the row, and then apply one-dimension DWT along the column, and then the result of these two sets of operations is a transform image with 4 distinct bands, which is LL, HL, LH, and HH. L is the low-pass filtering, and H is the high-pass filtering. So basically, again, you are applying in two, because image is a two-dimension, right? So you are actually applying in X direction and then followed by Y direction, that's all, okay? So this one I will explain later on in the next few slides. Details of the two-dimensional DWT process, we start with a mother wavelet, Ha or Duversis or Mollet, okay? You can actually find this one in MATLAB, okay? You can use different mother wavelet. The signal is then translated into shift or scale version of this mother wavelet. Okay, so this is what I going to explain about LL, LH, HL, and HH line. Okay. So this is the original input image. The gray color is the original, not original, but the backbone of this block diagram. So you have the original image, and then you have a. Please recall back. We apply the DWT in row and then followed by column, right? So which means you have apply in X direction and then followed by Y direction. So you have a horizontal approximation and horizontal detail. So sorry, okay, excuse me. So again, recall back the knowledge that we learned in previous slide. We have high frequency information which remark the details of X or Y or horizontal or vertical. We have low frequency information which remark the approximation. So in here, I use the word approximation and detail. Details, which means is referring to high frequency information, and approximation would be the low frequency information, whereby you just looking at the approximation, you could describe the meaning of this image, but the details is in high frequency information. Okay, so first of all, we apply the low pass filter, which means we apply on row first. So when we apply the low pass filter, which means low frequency information can pass through this filter. High frequency information will be removed, right? Low pass now. Okay, so after you apply the low pass filter, you would remove all the high frequency information. So what you get? You will get the horizontal approximation. And if you apply the high pass filter, you allow the high frequency information pass through the filter and remove away the low frequency information. Therefore, you will have horizontal diffuse. Okay, so later on, you apply again a low pass filter, you will able to get approximation. This is on the column. You apply low pass filter, so you will able to get the approximation image in both the direction, which is the x and y direction. Okay, but when you apply the high pass filter, you will get the vertical detail, y detail. So for the horizontal details, this is already consists of detail only image. So if you apply the low pass filter, you will have the horizontal details. And if you apply the high pass filter, which means you have x and y in detail. So this is described by the LL, LH, HL, and HH. Okay. So when you put LH and HL in different things, which means you apply the filter in row and column differently. Okay. So which means don't simply guess LH or LL because LH and HL is different thing. Okay. And the first layer we apply on row first, and the second layer we apply on the column. Okay. So the high frequency information is always dominant. So that is why when you have approximations and high frequency information in vertical, is dominant by the vertical. Okay, and you have high frequency information in horizontal and low frequency information in vertical, you will dominant by the horizontal. So this is how you get the. So from at the end of this wavelet transform, you will get 4 different images. The first one, approximate image, which is in x and y axis. The second one, the first one, approximate image, which is x and y axis, both are in approximate. Okay. The second one, vertical detail. The third one, horizontal detail. The fourth one, diagonal detail. Okay. So when you sum out the vertical detail and the diagonal detail, vertical detail and the horizontal details, you will able to get the diagonal. Okay. So this is how we actually get 4 of these LL, HL, LH, and HH. Okay. So wavelet analysis can be used to divide information of an image into approximation and details of subsignal. So these are the subsignal 1, 2, 3, 4. The approximation subsignal shows general trend of the pixel LL and 3 details subsignal, which is HL, LH, and HH. Okay, so the LL, actually you don't need to memorize this one because by knowing that apply low pass and low pass in both the horizontal and vertical direction, you should be able to know that by removing the high frequency information in horizontal and removing the high frequency information in vertical, you will get only the low frequency information in both vertical and horizontal. So by knowing LL, you should be able to know this is an approximation of the input image. And the same thing apply to HL, LH, and HH. Of course, you need to know you go to apply in what row or column first. Okay. If you are changing between row and column, you still can get 4 different kind of image. Just that maybe not exactly like this one. Maybe this one is referring to because you change this one horizontal detail to become vertical detail. So if you change this one, you would have a different LH will represent different kind, maybe the vertical image instead of maybe the horizontal image horizontal details instead of the vertical detail. Okay, so basically I don't suggest you all to memorize this one. So you have to know the theory behind, because the question may not be what is LL or something like that. Not something like that, because all these are application based. So please do not memorize things from lecture notes. For those definition, what is multimedia? This all of course you can memorize. But for this kind of application, please do not memorize because there is no solid rules how this filter can be applied. This is just an example for you all. Okay, always remember this one because you can actually change to start with column first followed by row. Okay, as long as you know low pass is to allow low frequency to pass through, then that will be fine. Okay, high pass to let high frequency to pass through, then should be sufficient. Okay, so if a signal is put through two filters, high pass and low pass filter, the signal is decomposed into this high pass filter, diffuse part, and the low pass filter, approximate part. Because high pass, because last time I cannot memorize, I cannot know high pass is actually remove high or let the high frequency to pass through. So actually it's very simple. High pass means only high frequency can pass through. Low pass is low frequency can pass through. That's all. Okay. So since you high pass, which means you allow high frequency to pass through, which means you would able to get the which means you will be able to get the only high the diffuse part. And if you allow only the low pass, the low frequency information, so you will able to get the approximate part. Okay. So at every level, DWT construct 4 sub-image, which is this 4 okay. And this 4 might not be the same. Okay. But anyhow, LL and HH would be the same. But the LH and HL might be different. Depends on row first or column first. So this is the original input image. So you apply low pass filter. So you subsampling by 2, and then you apply low pass filter again, subsampling, you will get LL, and then continue so you will get 4 LL, LH, HL, and HH. And from this 4, you can actually combine it together to form the approximate image. Okay, so we call this an approximate image is because this is an image where you approximate the original one. Okay, it is not identical because you already did the low pass filter. When you filter something, it is ideally it would be same, but actually in practical case, you would have trade off like the CMYK. Ideally, you have CMY you declare CMY as 1, you will get black color, right? But actually, in fact, in real life, this is not practical, whereby nothing is pure. So it's impossible for you to declare CMY as 111, then you will get a black color. Okay, so it's very tricky, RGB. If you set RG and B to 0, you get black color, right? So CMY is another case because you have to know the exit, the block exit X, Y, Z, and also CMY color box directions because you have different direction. CMY in 000 is not black color. Okay, CMY in 000 is white color. Okay, so you have to know why this is black, why that is why it is not white color. Okay. So basically, in MATLAB, we can actually illustrate using this one. This is just for illustration purpose. Okay, I think I will explain this one in next lecture. Yeah, I explain this one in the next lecture. Okay, so before we end, any questions? No? No? Any questions? Okay, so that's all for this lecture. And we do not have any tutorial for this because this is not with experience Wavelength. And the other thing tutorial should be maybe 4 because we have alternated one. So I will after tutorial 3 and 4. I will check that people for the purpose. The tutorial should be image manipulation. Okay. So I will do tutorial 3 and please something tutorial 3 next week. Thursday you will have videos. Okay. Thank you everyone and bye bye.